Welcome back to Quiet Science Journeys. A wave has left the sun, and Earth is beginning to feel it not as danger, but as a gentle stirring in our invisible sky. Tonight, we will follow that wave across space and listen for the moment our planet answers in light. We will move slowly in one long breath, letting facts feel like calm steps on a night path. Most days, sunlight feels steady, like a warm lamp over our lives. It pours across rooftops and rivers, and nothing about it seems hurried. We wake, we work, and we fall asleep under the same calm glow we have always known. So when the sun changes its tone, it can be easy to miss unless we listen carefully. The sun rises, warms oceans and cities, and seems to keep its distance. But it is a living star with tides of magnetism moving under its surface. And from time to time, those tides gather into a bright release. Recently, an upper M-class flare lifted from an active region on the sun. Along with the flash, a coronal mass ejection, a CME, unfurled into space. Think of it as a slow cloud of charged solar air expanding outward in all directions, and in this case, tending toward an Earth direct path. Not every solar cloud reaches us, but when one leans our way, our planet's magnetic shield listens closely. That shield, the magnetosphere, is an invisible bubble wrapped around Earth. It bends the solar wind around us like a shoreline bending an arriving tide. When a CME comes close, the bubble compresses and flexes, and the energy it absorbs can travel through the upper atmosphere. Sometimes the effect is quiet, a small ripple in instruments. Sometimes it is strong enough to widen the auroral zones, and then the night sky answers with color. At nearly the same time, Earth has been moving through its own release. USGS recorded a magnitude 7.0 earthquake in Alaska, followed by a thick scatter of aftershocks. Alaska sits on a restless edge between tectonic plates and aftershocks. There are part of the crust settling into a new balance. In another layer, still some observers noticed an unusual pattern in Schumann resonances, the faint electromagnetic hum between Earth and the ionosphere. Public scientific confirmation of that pattern is limited, so we will hold it gently as a note rather than a conclusion. And in the volcanic realms, Kilauea has also been active during this broader interval, reminding us that Earth has many ways of expressing its energy. These are separate threads. We will not tie them too tightly. We will simply notice them together, the way nature sometimes stacks moments in the same span of days. If you are listening from a high latitude, you may have a chance over the next night or two, around the arrival window, to see Aurora reach farther from the poles than usual. If you are not, that is fine too. The point of this journey is not to chase a spectacle, but to understand a living system, and to let that understanding feel calm. So settle in. Let your shoulders drop. Let your breath soften. We are going to trace how solar storms form, how NOAA reads them, how Earth responds, and why USGS keeps watch on the ground beneath us. We will move from the sun, through space, down into the planet's crust, and back out to the quiet sky. Along the way, we will keep our feet on the ground of evidence and let curiosity be warm rather than urgent. It is the difference between running after news and resting inside a story that is already unfolding. For now, imagine the sun far away, bright and restless, and Earth here below, steady and listening. We begin with the star. Tonight's journey has a simple shape, and I will keep it gentle. We will move through 3 layers of one living system. First, we will stay with the sun and the quiet space around it. We will look at what an upper M-class flare is and how a coronal mass ejection can lift away as a slow cloud of charged plasma. We will follow the cloud's path and notice why an Earth-direct direction matters not as a reason to worry, but as a reason to pay attention. We will also touch the wider rhythm of sunspots and the solar cycle, because a single flare makes more sense when you can feel the longer melody beneath it. When you see an event as one note in an 11-year rhythm, it stops feeling random and starts feeling like part of a living, breathing star. Second, we will come home to Earth. We will sit with what USGS recorded in Alaska, a magnitude 7.0 earthquake, and a dense aftershock sequence. We will let the science be clear, and calm earthquakes are mainly stories of tectonic stress, building over long spans of time, then releasing in moments. Aftershocks are the crust adjusting its balance like small, settling breaths after a deeper exhale. When timing overlaps with solar activity, it can feel meaningful, but timing is not causation. We will hold curiosity in one hand and evidence in the other, and keep both hands relaxed. If there are connections in nature, they reveal themselves through careful patterns, not through a single coincidence. Third, we will lift our eyes back to the night sky. If the incoming CME couples strongly with Earth's magnetic field, NOAA expects a geomagnetic storm centered around G3 conditions, with a smaller chance of a brief G4 peak if the magnetic orientation turns favorable. We will talk about what the G-scale means in simple terms and why forecasts are always a range until the cloud arrives close enough to measure directly. Then we will translate that invisible space weather into something you might actually notice the possibility of Aurora reaching farther from the poles and the quiet reasons behind its colors and motion. By the end of our journey, you will know what this storm really is, how NOAA and USGS read it, and why the Sun and Earth keep speaking this way. And if you feel like looking up later, you will also know exactly how to watch for Aurora quietly, simply without chasing headlines. As we move through these layers, I will keep the pace slow enough for rest. Facts will arrive like soft footsteps, not like alarms. When something is uncertain, I will say so. When something is well measured, I will anchor it to that measurement. And when 2 events share the same window of time, I will let them sit beside each other without forcing a chain between them. That is how we keep wonder alive without drifting away from reality. You do not need to hold every detail. You only need to drift with the shape of the story. A star releasing a wave, a planet receiving it, another kind of weather in the air, another kind of motion in the ground, and sometimes a quiet glow in the sky that reminds us we live inside a larger, softly changing environment. So, let your attention soften. Let the room around you blur at the edges. We are about to step back toward the sun, to the place where this wave began, and to the calm physics that let it unfold. A recent upper M-class flare rose from an active region on the sun, and that simple sentence holds a great deal of quiet physics. To begin, let's picture the sun not as a flat disk in the sky, but as a vast sphere of hot plasma threaded through and through with magnetic fields. Those fields are not decorations. They are the sun's inner weather, shaped by the motion of charged gas rising, sinking, and flowing beneath the surface. Where the magnetism becomes tangled and strong, it can press down on the visible surface and form sunspots, darker regions that are not cold in any human sense, simply cooler than the surrounding plasma. Sunspots are markers of magnetic complexity, and magnetic complexity is where flares are born. A solar flare is the sudden brightening that occurs when magnetic field lines twist too far, then reconnect and release stored energy. Reconnection is one of those quiet, universal processes. It is the way the cosmos relaxes tension in magnetic fields, from stars to planets to distant nebulae. On the sun, reconnection can happen in minutes, and the energy it releases appears as radiation across the spectrum, especially in X-rays and ultraviolet light. In the language of space, weather flares are classified by their peak X-ray output. You may have heard the classes before. C-class flares are relatively small and common. M-class flares are stronger, capable of producing noticeable effects if they are aimed our way. X-class flares are the largest, rarer peaks of solar activity. This recent event falls in the upper M-class range, meaning it is near the high end of what the M category contains. That is significant, not because it implies catastrophe, but because upper M-class flares often have enough energy to lift a coronal mass ejection into space. A flare is light and radiation. A CME is matter and magnetism. They can happen together, but they are not the same thing. You can think of the flare as the flash of a door opening. The CME is what steps out through the doorway. A coronal mass ejection begins in the sun's outer atmosphere, the corona, where magnetic loops arch high above sunspot regions. Sometimes those loops become loaded with plasma, and sometimes they become unstable. When the magnetic structure can no longer hold its shape, it lifts away, carrying plasma and its embedded magnetic field into interplanetary space. In imaging, this appears as an expanding cloud, often with a rounded front and a faint cavity behind it. In this case, the CME emerged in a way that models describe as Earth direct or close to Earth direct. That does not mean it is aimed like a laser. Space is wide. CMEs expand like umbrellas. But an Earth direct CME is one whose central trajectory is near the line between the sun and our planet. It is the difference between a wave that spreads out in the ocean and a wave that is angled toward your shoreline. You might still feel only the gentle edge, or you might feel a fuller surge, but the probability of feeling it rises. How do we know it is aimed our way? We watch it from multiple angles. Solar observatories use coronagraphs, instruments that block the bright disk of the sun, so we can see the faint corona. When a CME lifts off the coronagraphs, show it moving outward as a widening halo. If the halo appears symmetric around the sun, that is a hint of a full halo CME, meaning the cloud is coming toward or away from Earth, not mostly sideways. Other telescopes view the eruption from slightly different perspectives, and by combining views, scientists estimate the CME's direction and speed. In differential imagery, where each frame is subtracted from the previous one motion, becomes easy to see. The eruption appears as a bright front, expanding through darker background. Over successive frames, the front grows, and sometimes you can see a subtle double structure, a leading shock, and a denser core behind it. We will linger with that structure more in a moment, but for now, hold the main idea. Something has left the sun. It is traveling through space, and its path leans toward us. The time it takes to arrive depends on its speed. Fast CMEs can reach Earth in a little over a day. Slower ones can take 2, 3, even 4 days. Speed estimates are made by tracking the CME's expansion in coronagraph views and feeding those measurements into models. These models also account for the background solar wind because a CME does not travel through empty space. It moves through a flowing stream of particles already leaving the sun. That stream can slow it down or sometimes help carry it along, depending on its relative velocity. This is why forecasts include a window, not a single minute. Even with good data, solar wind conditions vary, and small differences accumulate over millions of kilometers. The closer the CME gets, the tighter the window becomes. Now, before we follow the cloud outward, it helps to notice something about the region that produced it. Active regions often release energy in clusters. A smaller flare can occur, first loosening the magnetic field. Then a stronger flare can follow as the region continues to reorganize. Think of it like a tight knot being worked gently at first, then suddenly giving way. Not every region follows this pattern, but it is common enough that observers watch for it. In the current window, an earlier M-class flare preceded the stronger upper M-class event. That earlier flare may have launched a smaller puff of plasma as well, but the main Earth-directed CME appears tied to the stronger flare that followed. This is not stated to dramatize. It is stated because it tells us the magnetic region is active and capable of multiple releases. Active regions are living things by solar standards. They grow twist decay and sometimes flare repeatedly over several days. As long as they face Earth, the probability of further flares remains elevated. Once they rotate away over the limb, that probability drops from our perspective. But even then, the sun is rotating, and what leaves view will return around the far side in about 25 days. We are in a part of the solar cycle where sunspots are more numerous than they are during quiet years. The sun follows an approximately 11-year rhythm, rising from minimum to maximum and back again. In rising years, sunspot counts increase, active regions become more common, and eruptions like this happen with greater frequency. This does not mean every day is stormy. It means the baseline odds are higher. An upper M-class flare in this phase is a note in a longer melody, not an isolated surprise. That longer rhythm matters for how we feel these events. When you know the sun is moving through a cycle, a flare is less like a random accident and more like a seasonal wave. It belongs to a pattern that has repeated many times and will repeat many times again. We can still be curious about each individual event, but we do not need to treat it like a once-in-a-lifetime interruption of normal life. This is normal life in a solar system with an active star. So right now, we have an upper M-class flare behind us and a CME traveling outward toward us. Those are the rooted facts. Anything else is about probability, and probability is what space weather agencies specialize in translating. Before we go there, Let's deepen our understanding of what a CME carries. A CME is not only a cloud of particles, it is also a magnetic structure. The plasma in a CME is threaded with an interplanetary magnetic field. That field is born from the sun's own magnetism and takes its orientation with it as it travels. The CME can be imagined as a twisted rope of magnetic field lines wrapped around a denser core of plasma. The orientation of that rope and how it rotates as it travels is what finally decides how strongly Earth responds. From far away, we can estimate the CME's speed and density. We can estimate its width and direction. But the internal magnetic orientation, whether its field will point northward or southward relative to Earth when it arrives, is harder to know until it is close. The sun gives hints, but the path through space can also reshape the cloud. This uncertainty is why a strong flare does not automatically equal a strong geomagnetic storm. A CME can arrive fast and dense, but with a magnetic orientation that couples weakly with Earth producing only moderate effects. Another CME can arrive with a gentler speed, but a deeply southward field and produce a stronger storm than expected. So, when we say this CME is Earth-directed, we are describing geometry. When we say a G3 storm is likely, we are describing probability based on speed density and typical behavior of similar clouds. And when we wait for arrival to see the true magnetic orientation, we are describing a final key that cannot be turned until the cloud is at our doorstep. That is the honest science. Now, as the CME moves away from the sun, it does not travel as a single smooth shell. It travels more like a tide with layers, and those layers matter when they reach Earth. When scientists look at coronagraph imagery, especially differential views that highlight motion, a CME often appears in two main steps. First, there is the leading shock wave. This is the bright front that races ahead of the cloud, compressing the ambient solar wind. Space is thin, but it is not empty. The solar wind is always flowing outward from the sun, a river of charged particles filling the solar system. When a CME is faster than that background river, it creates a pressure wave in front of it, much like a boat makes a bow wave as it cuts through water. The shock wave is not the main body of the CME. It is the first disturbance, the first push. If you imagine Earth's magnetosphere as a quiet shoreline, the shock wave is the first swell to touch it. The shoreline flexes inward, and the system notices the change quickly. Behind the shock wave comes the bulk of the plasma. This is the denser heart of the CME itself, the core cloud, carrying more mass and more embedded magnetic structure. In imagery, it often looks like a broader, thicker front, following behind the shock sometimes with a faint cavity or trailing material. When this core arrives, it can sustain pressure on Earth's magnetic boundary and feed energy into it over a longer span of time. So, a two-step arrival looks like this: a fast push, then a heavier follow-through. Not every CME presents both layers clearly. Some eruptions are weaker, more like a soft puff. Others are wide but thin. Some are fast but not dense. But upper M-class events often produce CMEs with enough speed and mass to form a distinct shock front. Why does this matter so much for geomagnetic storms? Because Earth's response depends on pressure, and pressure depends on both speed and density. If the shock wave arrives alone, you might get a quick compression of the magnetosphere, then a return toward normal if the core is faint or missed. The storm can be brief and modest. If the shock wave is followed by a dense core, you get a sharper compression that is sustained. Energy continues to flow in. The magnetosphere stays pressed and active. That is when storms rise into stronger categories and aurora becomes more likely to spread. In modeling for the current event, forecasters expect a noticeable rise in solar wind velocity as the shock arrives and a jump in plasma density as the core follows. That combination is a classic signature of a more meaningful geomagnetic response. Still, even with speed and density, the last key is magnetic orientation. The core of a CME carries an interplanetary magnetic field, and when that field meets Earth's field, the two can either connect well or resist each other. The strongest coupling usually happens when the incoming field points southward relative to Earth's northward field on the day side. Southward orientation opens a pathway for energy transfer. It is like two puzzle pieces aligning. If the incoming field points northward, the pieces do not align as easily. The magnetosphere still compresses from the pressure, and storms can still occur, but energy transfer is less efficient. Aurora may remain more confined to high latitudes. The storm may stay closer to G2 than G3, even with a strong shock. From far away, we cannot know the exact orientation the core will present at Earth. The cloud may rotate as it travels. Its internal rope can twist. Those details remain hidden until the CME is close enough to measure directly with satellites upstream of Earth. So the layered structure gives us a reason to expect a stronger response. But the true final outcome still waits at the moment of arrival. There is another subtle thing the two-step structure does. It changes timing. A shock wave can arrive hours before the densest core. In that interval, Earth can begin responding even before the main cloud reaches us. This is why storm forecasts often include a longer arrival window. The first signs can begin with the shock and then intensify with the core, depending on how close together they are. Sometimes, the shock and core arrive nearly back-to-back, producing a quick surge of activity. Sometimes, they are separated enough to create two distinct phases, a first bump and a second rise. Either way, the magnetosphere treats the arrival as a process, not a single instant. If you follow solar wind plots in real time, you can often see this story unfold. A sudden rise in speed, a sharp increase in dynamic pressure, then a denser stream of particles. And within those streams, the magnetic field direction wavering, then settling southward or not. Those are the quiet instruments of space weather, but you do not need instruments to respect the beauty of it. Think of the CME as a traveler made of two footsteps, a lighter foot that arrives first, a heavier foot that follows. Earth hears both. Earth bends to both, and when the bending is deep enough, the atmosphere near the poles becomes a stage for aurora. Particles spiral downward along magnetic field lines. They collide with oxygen and nitrogen high above. The atoms glow as they relax. Green, low red, higher blues, and purples faintly mixed in. A silent choreography in the air. So, in this moment, as we wait for arrival, what we truly know is simple. The CME has left the sun. It is traveling in our direction. It carries a likely shock front and a dense core. It is expected to raise solar wind speed and density as it arrives, and its magnetic orientation will decide how strong the storm becomes. That is enough to hold with quiet confidence. Before we leave the sun behind, it helps to stay with the surface for one more quiet moment, because the surface tells us what the deeper magnetic weather is preparing. Sunspots are not just dark marks. They are the places where the sun's magnetic field rises up through the photosphere tight and concentrated. That concentration limits convection, so the region looks darker than its surroundings, but it is still unimaginably hot. The darkness is only relative. What matters is what the darkness signals. It signals tension. It signals twist. It signals stored energy. When sunspot numbers rise, it means more magnetic knots are appearing on the sun at once. Not every knot will flare, and not every flare will launch a CME, but the background odds change. The sun becomes more talkative. Right now, sunspot activity has been elevated compared to the quietest years of the cycle. You can think of this as a season, not a surprise. In rising phases, the sun shows more complex regions, and those regions sometimes release energy in clusters. One release can be small, another larger, and all of it belongs to a larger rhythm. The sun moves in an 11-year rhythm. In the rising years of a cycle, sunspots cluster more often, and eruptions become a little less rare. This event is one note in that longer melody. That melody is important for the way we hold this moment. If you picture solar activity as random, each flare feels like an interruption. But if you picture solar activity as cyclic, each flare feels like weather in a season. Sometimes a season is calm, sometimes it carries more storms, and none of it is personal. It is simply the sun doing what active stars do. The active region that produced the recent upper M-class flare remains capable of further releases as long as it faces Earth. Active regions are like temporary cities of magnetism. They grow, reorganize, and decay over days. Some burn bright once and fade. Others flicker repeatedly, as if the system is gently trying to untie itself from the inside. Forecasts for the next few days stay watchful because the region still carries complexity. Another flare could occur. Another smaller CME could lift away. Or the region could quiet down and simply rotate onward. We do not pretend to know which path it will choose. We only know the probability is higher while it is still in view. There is also a large sunspot group that has been quiet. Large does not mean immediate. Sometimes a group forms quickly, but needs time to organize before it becomes eruptive. Sometimes it stays quiet for its whole passage across the visible disk. And sometimes, after it rotates away and returns about 25 days later, it comes back in a different mood. The sun is not a machine with a single switch. It is a fluid system with memory and momentum. A quiet region today can mature into an active region later. An active region today can unwind and fade by tomorrow. So when you hear that sunspots are numerous or that a region is large, what you are hearing is a description of possibility, not a guarantee. It is the state of the canvas, not the brushstroke that will be painted next. This is why space weather forecasting is patient. Observers track sunspots, estimate their magnetic classification, and watch for signs of instability such as increasing shear along the neutral line or emerging flux that distorts the local field. Those details are technical at the edges, but the spirit is simple. We watch for whether a region is storing energy or releasing it. We watch for whether it is tightening or loosening. And while all of this happens, Earth keeps orbiting in its quiet lane. We do not need to do anything special. We do not need to brace. We only need to notice that the star we live with is alive, and that its moods come in cycles we can learn to recognize. If you listen to these updates, often your sense of solar time becomes more natural. You start to feel the sun's rotation the way an active region drifts from the east limb to the center, then toward the west. You start to recognize that an 11-year cycle is a long breathing pattern, and that within that breath, there are smaller pulses, flares and clouds that rise and travel. For tonight, all we need is to hold a simple truth. We are in a more active season of the solar cycle. A capable region has sent an upper M-class flare and an Earth-directed CME. It may send more, or it may rest. And one quiet region may return later with a different story. That is the surface view. Now, we translate the solar story into the language that space weather agencies use to describe Earth's response. They call it the G scale. The G in G scale stands for geomagnetic, and the scale runs from G1 to G5. It is not a scale of drama. It is a scale of probability and expected intensity based on how Earth's magnetic field behaves when the solar wind presses in. G1 storms are minor. They are common and usually gentle in their effects. G2 storms are moderate, a little stronger, and still within familiar ranges. G3 storms are strong. They can widen Aurora and create noticeable disturbances in some systems. G4 storms are severe, less common, and typically brief unless driven by a very large cloud. G5 storms are rare extremes, the kinds that show up only a handful of times in a solar cycle. The scale is built from measurements of Earth's magnetic field, especially how much it wavers from its calm baseline. Those measurements are summarized in planetary indices, and from those indices, agencies estimate what level of storm activity is most likely as a CME arrives. In this current window, the central expectation from NOAA is a geomagnetic storm centered around G3 conditions. That is the middle of the forecast. It is the most likely lane, but forecasts also include edges. Some models allow for a brief G4 peak if the magnetic orientation inside the CME turns favorable for strong coupling. This is not a contradiction. It is the nature of forecasting when one key variable is still unknown. Until the cloud arrives close enough to measure directly, we hold a range rather than a verdict. The last detail we wait for is the magnetic direction inside the cloud. Until it arrives, we hold a range, not a verdict. This is the quiet heart of space weather prediction. The speed and density of the CME give us one part of the picture. They tell us how much pressure the magnetosphere may feel, but the interplanetary magnetic field carried by the CME tells us how easily energy can enter Earth's system. The most important component of that field is the north-south direction, often called BZ. If B's point southward for a sustained span, coupling is strong. Earth's magnetosphere opens more easily on the day side and energy transfer rises. Storm levels climb. Aurora expands. If B's points northward or flips quickly between directions, coupling is weaker. The magnetosphere still compresses, but less energy enters. Storms remain milder. Aurora stays closer to the poles, so when NOAA centers a forecast on G3, they are saying this. Based on speed density and typical behavior of similar CMEs, a strong storm is likely. When other models mention a chance of G4, they are saying this. If BZ turns strongly southward, a brief severe peak could form. Both statements can be true at once because they live inside probability. When the CME finally reaches the near-Earth environment, satellites stationed upstream, such as those at the L1 point, measure the real-time solar wind. That moment is when the range collapses into a clearer lane. If you ever watch live plots, you will see the decision take shape. A rise in speed, a jump in density, then the magnetic field direction settling into south or not. The storm is not decided by a single number. It is decided by a moving pattern. Now let's place this storm in a wider context, because context is what keeps the mind calm. Earth has seen storms far stronger than this, even in living memory. Compared to those rare extremes, a G3 storm is a firm but familiar tide. Strong storms happen in most solar cycles. They are part of the expected dialogue between an active star and a magnetized planet. They can be beautiful, sometimes inconvenient, and occasionally technically challenging for certain systems, but they are not an alien event. They are a kind of cosmic weather that Earth has met many times. This perspective matters because online space weather talk often swings between two extremes. Either everything is framed as nothing at all, or everything is framed as an emergency. The reality lives in the middle. A G3 storm is worth noting. It is worth watching. It can widen Aurora and make the night sky feel larger. But it is also within the familiar envelope of strong storms that our systems are built to handle. If there is a brief G4 peak, that would still be a peak inside a short event, not a prolonged crisis. G4 levels usually require strong, sustained southward fields inside a dense cloud, and in many cases, the peak lasts hours, not days. If you live at mid-latitudes, G4 can bring Aurora a little farther south. If you work with communication systems or satellites, it can make conditions noisier. But for most people, it is simply another reminder that Earth lives inside a magnetic sea. So the G-scale does two things at once. It protects us from exaggeration, and it protects us from indifference. It gives a measured way to say this storm is likely to be strong enough to matter, but not so strong that it breaks the rhythm of ordinary life. If you are sleeping as you listen, you do not need to remember the numbers. You only need to feel the shape. A wave approaches. We expect a strong response. A stronger peak is possible if the wave carries the right magnetic tilt. That is all. In practical terms, here is what a G3-centered storm usually brings. Aurora becomes more active at high latitudes, and the auroral oval widens. It can dip into the northern United States and across higher parts of Europe, and it can brighten enough to be seen by the eye in darker skies. If you are farther south, cameras may pick up a faint glow, even when your eyes see only a soft haze. High-frequency radio paths can become less reliable. This matters for certain aviation and maritime routes, and for hobbyists who listen to shortwave. During strong storms, the ionosphere is more disturbed, and radio signals reflect differently. Satellites can feel slightly increased atmospheric drag. The upper atmosphere warms and expands under geomagnetic forcing, which raises density a bit at orbital altitudes. Operators account for this, sometimes adjusting their models and schedules. Power grids monitor geomagnetically induced currents. Strong storms can drive small currents through long conductors, especially at higher latitudes, and utilities have protocols for adjusting load and configuration if needed. All of these are normal protective measures in a system that understands its environment. You might notice none of this from your bed, and that is fine. The purpose of knowing is not to stay awake. The purpose of knowing is to rest inside reality. So as we move forward, keep both truths together. No AA centers expectation on a G3 storm as the CME arrives. A brief G4 peak is possible if the magnetic orientation turns strongly southward. The final decision waits at arrival when satellites read the field directly. And whatever the outcome, it sits inside the familiar range of strong geomagnetic weather. As the CME reaches the near-Earth environment, the story becomes less about the sun and more about the boundary that surrounds us. That boundary is the magnetosphere. It is not a hard shell. It is a living shape made of field lines and charged particles, constantly adjusting to whatever the solar wind brings. Most of the time, it holds steady in a gentle balance. But when a strong wave arrives, the balance shifts. I like to picture the magnetosphere as a quiet shoreline. When the solar wind presses in, the shore doesn't break it. Flexes stores the push for a while, and then releases it as gentle waves. The first press often comes with the CME's shock wave. Upstream satellites feel it first. They register a sudden rise in solar wind speed and a sharp increase in dynamic pressure. That pressure is simply a measure of how forcefully the solar wind is pushing. When it rises quickly, the magnetosphere is nudged inward, like a beach, responding to a stronger incoming swell. This inward flex is not a failure. It is what the system is designed to do. Field lines on the day side compress. On the night side, they stretch into a long tail. This tail, called the magnetotail, is where energy can be stored for a time. The solar wind is a flow, and Earth's field is a shape inside that flow. When the flow strengthens, more energy is loaded into the shape. After the shock comes the core. The denser plasma arrives, and the solar wind pressure stays elevated. In a strong event, this is when the magnetosphere remains pressed rather than bouncing back quickly. It is also when the interplanetary magnetic field inside the CME becomes the central character. The key part of that field is its north-south orientation. If the incoming field points southward for a sustained stretch, it couples efficiently with Earth's field. The link happens on the day side, where Earth's northward field meets the CMEs southward field. They reconnect, opening a door for solar wind energy to enter. That energy does not pour straight down to the ground. It moves through the system. It flows into the magnetotail, then is released in pulses back toward the poles. Those pulses drive currents in the upper atmosphere called auroral electrojets, and those currents help shape the auroral oval. If the incoming field points northward, the door is mostly closed. The magnetosphere still flexes from pressure, but less energy is handed inward. The shoreline is still touched by the swell, but it does not roll as deeply into itself. This is why two storms that look similar in coronagraphs can feel different at Earth. The same speed, the same density, but a different magnetic tilt. One couples strongly and makes the sky bright. Another passes with only a mild stirring. In the arrival window, the magnetosphere is doing three things at once. It is being pressed inward by pressure. It is being connected or resisted by magnetic direction. And it is redistributing whatever energy enters across the upper atmosphere. This redistribution is not smooth. It is rhythmic. Energy loads, then unloads. The auroral oval widens, then contracts. The sky brightens, then softens. You can imagine it like breathing, inhaling as the solar wind pushes, holding as the magnetotail stores, exhaling as energy releases toward the poles. When the release is strong, charged particles spiral down along magnetic field lines. They meet the thin air high above mostly oxygen and nitrogen, and they excite those atoms into brief states of higher energy. As the atoms relax, they emit light. The process is gentle. The effect is luminous. Green is the most common shade because oxygen at lower altitudes produces it efficiently. Red appears higher up, where oxygen relaxation is slower and the air is thinner. Purples and blues come from nitrogen, often faint, sometimes more vivid at the edges of active curtains. The colors are not paint in the sky. They are atoms resting back into themselves. This is the magnetosphere's answer. A conversation between a star and a field, a tide and a shore. And if you are wondering whether all of this can affect us directly on the ground, the answer is that most of it stays far above. The atmosphere and magnetic field are a cushion. They are part of Earth's design. The practical effects we mentioned earlier, radio variability, satellite drag power, grid monitoring, all arise as gentle consequences of currents in the upper air, not as direct impacts on daily life. So while the system is active, your room can stay quiet. You can let the idea of waves and shores be enough. A wave presses in. A shoreline flexes. Energy gathers, then releases. Light appears in the high air, and whether you ever see the light or not, the process is happening with a steady kind of beauty, the sort that does not demand attention, but rewards it. Most of what we have described so far happens far above the world we touch. A geomagnetic storm is a high-altitude event. It lives in the magnetosphere and the upper atmosphere where the air is thin and the fields are strong. For most people, the storm is something you can sleep through without ever noticing, and that is a comforting truth. Still, It helps to know the gentle ways a strong storm can show itself, not to alarm you, but to place this moment inside the normal range of Earth's space environment. The most visible effect is aurora. When the magnetosphere is pressed and coupling is sustained, the auroral oval widens. High-latitude skies become more active, and places that are usually just outside the aurora zone can slip inside it for a night or two. This widening is why a G3-centered storm matters to sky watchers. It does not guarantee a bright show everywhere, but it increases the chances for those nearer the poles and sometimes offers a faint glow for those farther away. Some people will see moving curtains and arcs with the naked eye. Others will see only a soft brightening near the horizon. Cameras may catch more than eyes can in dim conditions, especially in long exposures. The second effect is quieter and mostly noticed by those who work with radio. High-frequency or shortwave radio signals travel by reflecting off the ionosphere. During geomagnetic storms, the ionosphere becomes more disturbed. Its density changes, and those changes can make radio paths shift or fade. For aviation and maritime routes that depend on HF links, this is a routine part of space weather awareness. For hobbyists who listen to distant broadcasts, it is simply a night when the bands behave differently. The third effect touches spacecraft. When geomagnetic energy enters Earth's upper atmosphere, it can warm that thin air. Warm air expands, and the expansion increases atmospheric density slightly at orbital altitudes. Satellites, especially those in lower orbits, may experience a bit more drag than usual. Operators anticipate this. They update models, and if needed, adjust orbits gently over time. It is not a crisis. It is maintenance in a living environment. The fourth effect is something utilities watch closely. Geomagnetic storms drive currents in the upper atmosphere, and those currents can induce tiny companion currents in long conductors on the ground. Power grids at higher latitudes monitor for these geomagnetically induced currents, and they have protocols to reduce risk. Adjusting load watching transformers and staying alert during strong storms is normal practice. Earth has been through countless storms, and our modern systems have learned the patterns, so the picture is calm. Aurora may widen. Radio conditions may shift. Satellites may feel a soft increase in drag. Power operators may stay watchful. None of these effects are meant to pull you out of rest. They are simply part of the way a magnetized planet lives under an active star. And in a deeper sense, storms like this are one of the ways we learn about our own protective shell. The magnetosphere is not only a shield, it is an instrument. When the solar wind plays on it, we hear its shape and data and see its glow in the sky. Each storm teaches us how Earth responds and how resilient the response can be. This is why agencies forecast in ranges rather than absolutes. It is why they watch speed density and magnetic direction as the cloud arrives. And it is why a G3 storm, even when it feels quiet to most of us, is still worth noticing. Not because it is dangerous, but because it is one of the many ways the solar system shows that it is alive. Now, we come down from the upper air to the ground beneath us, to a kind of energy that moves more slowly and sometimes speaks in sharper moments. USGS recorded a magnitude 7.0 earthquake in Alaska during this broader interval. The number is large, but the meaning is older than the moment itself. Earthquakes are not sudden inventions. They are the release of stories that have been forming under the surface for years. Alaska sits along one of the most active tectonic boundaries on the planet. It is part of the vast ring of subduction and collision that edges the Pacific, where plates meet, press, and slip. The crust there is not quiet, because the plates are not quiet. They are always moving millimeter by millimeter, carrying continents and ocean floor, as if on slow conveyor belts. Most of that motion is smooth. Some of it is not, along faults. Friction holds plates in place, while stress accumulates behind them. When the stress exceeds the strength of friction, the fault slips. Rocks that were locked suddenly move, and the energy stored as strain is released as seismic waves. Those waves travel through the crust, the mantle, and sometimes even through the whole globe. They are the ripples of a deep physical exhale. A magnitude 7.0 earthquake is a strong one. It means a fault segment released a substantial amount of stored stress enough to send energy widely through the region. In Alaska, such events are a known part of the tectonic landscape. They are not daily, but they are within the expected range for a subduction and transform boundary system built on constant motion. After a main shock of this size, the crust does not instantly return to stillness. It has to settle. That settling appears as aftershocks. Aftershocks are smaller earthquakes that occur in the minutes, hours, days, and sometimes weeks after the main event. They happen because the main slip redistributes stress. Some areas near the rupture are relieved. Others are loaded more heavily. The crust adjusts to this new pattern, and in that adjustment, smaller slips occur. In Alaska's case, the aftershock sequence has been dense with many events in the magnitude 4 to 5 range. For people nearby, this can feel like the ground is reluctant to fully fall quiet. You may feel sharp jolts, brief rolling sensations, or a subtle, persistent sense that the earth is still working something out beneath your feet. For the crust, this is normal. A dense aftershock swarm usually means the system is doing what systems do after a big release. It is searching for a new balance. Think of a tree in heavy wind. When the biggest gust passes, the branches do not freeze instantly in place. They sway, rebound, and sway again before resting. The same logic lives underground. You may hear a phrase like the strong aftershock is usually about 1 magnitude smaller than the main quake. That is a rough statistical rule. It is not a guarantee, but it is a helpful expectation. When a magnitude 7 occurs, aftershocks in the high fives are within normal bounds. The presence of many magnitude 4s is also typical. What looks like a swarm on a map is often the crust doing its slow accounting. Seismologists watch aftershocks closely because their pattern can tell a story. The distribution of sizes, the way locations cluster along faults, the way the sequence decays through time, all of these reveal something about the rupture and the ongoing stress field. But for our purposes tonight, the meaning is simpler. A big release happened. The ground is settling. This settling can take time. It is also worth remembering that seismic energy travels far beyond what we feel. Seismometers are exquisitely sensitive. They can detect ground motion that is far too small for human perception. After a magnitude 7 instruments across North America and often across the hemisphere register waves passing through. The waves can circle the globe. They are part of the Earth's low, slow conversation with itself. If you are far from the epicenter, you will not feel those waves. But they are still there, threading through the planet like the fading hum of a bell after it has been struck. In Alaska, the tectonic setting makes long aftershock sequences plausible. The region is shaped by the interaction of multiple plates and fault systems, and stress there is not distributed evenly. An earthquake in one part of the system can change stress in another. That is why seismologists consider regional context not only the single rupture. Alaska also experiences frequent smaller events, even in quiet times. The crust there is always adjusting. When a large quake happens, it is a peak in that ongoing adjustment, not a separate phenomenon. Sometimes, before a main shock, there are precursor events. A magnitude 6 in a nearby setting or odd behavior in an aftershock sequence can reflect broader regional stress dynamics. These patterns are subtle and not always predictive. In science, we treat them as hints, not certainties. We examine them after the fact to understand the system better, and we use that understanding to refine future probabilities. So, what should we take from this Alaska earthquake tonight? We take 3 calm truths. First, it was a real tectonic event. Its main driver is the slow but relentless build of plate stress along a boundary region. Second, the aftershocks are a normal part of the crust settling. A dense swarm is not necessarily a sign of escalation. It is often a sign of adjustment. Third, the event belongs to Earth's larger rhythm. Just as the sun has cycles of activity, Earth has zones of persistent tectonic motion. Neither rhythm is a personal message. They are the way physical systems behave over long time. If it helps, you can hold an image. Imagine the Earth's crust as a mosaic of moving pieces. Most of the time, the movement is so slow you cannot sense it. And then along one edge, a piece slips, releasing years of stored tension in a single hour, followed by smaller slips as the mosaic settles into a new arrangement. This is not a sign of a planet that is breaking. It is a sign of a planet that is alive. And while it can be unsettling for those who live close to the event in the broad view of geology, it is part of a known and expected process. Tonight, we are holding the quake beside a solar storm, not because one caused the other, but because they shared a window of time. We allow them to sit together without tying a knot between them. That quiet restraint is what keeps science trustworthy. When two powerful events share the same span of days, it is natural for the mind to wonder whether they are connected. Wonder is not a mistake. It is one of the ways we stay awake to the world. But in science, wonder has to walk alongside evidence. So let's say this clearly and calmly. Timing is not causation. A solar flare and a CME are expressions of magnetic energy in the sun's atmosphere. An earthquake is a release of tectonic stress inside Earth's crust. They happen in different layers of nature, driven by different primary forces. Earthquakes are mainly internal stories. Plate motion is slow but relentless. It loads stress along faults for years or decades. Friction holds that stress in place until a threshold is crossed, and then the fault slips. The energy released in that slip is vastly larger than any short-term external influence we know how to measure. Even when we see patterns in global seismicity over longer spans, the core driver remains the same. Stress builds. Stress releases. Space weather acts in different places. A CME changes conditions in the magnetosphere and upper atmosphere. It can disturb the ionosphere, shift electric currents in high air, and drive auroral activity. These are real and measurable things. But they are not the same as pushing a fault to slip in a specific location at a specific hour. A direct, short-term trigger from a single solar event to a particular earthquake has not been demonstrated in the scientific literature. That does not mean we stop asking questions. It means we ask them in the right way. Researchers do explore broader links between space weather and Earth systems. Over long timescales, there are hypotheses about how geomagnetic activity might modestly modulate atmospheric circulation, or how changes in the ionosphere might correlate with certain geophysical signals. These are complex topics. The effects, if they exist, are subtle, statistical, and embedded in many confounding variables. They are not simple levers. So if a quake and a flare happen near each other in time, the honest posture is to notice the coincidence, then step back. We hold two thoughts at once. One, nature is a network of interacting systems, and sometimes those interactions reveal themselves in ways we have not fully mapped yet. Two, we do not claim a connection until the connection can be shown through careful patterns, repeatable evidence, and a mechanism that holds under scrutiny. This is what keeps science from drifting into story for its own sake. It is also what keeps the mind calm, because when everything is connected in a vague way, everything can feel ominous. But when we respect the boundaries of evidence, the world feels stable again. We can admire multiple events in the same window without turning them into foretold meaning. So tonight, we let the solar storm be what it is: a magnetized cloud from an active star approaching Earth's magnetic shore. And we let the Alaska earthquake be what it is: a tectonic release in a region built on long-term plate motion. They may share a week. They may share our attention. But they do not need to share a cause. This kind of careful separation does not reduce wonder. It refines wonder. It lets us be curious without being pulled into certainty, where certainty is not earned. Now, we step into a layer that is quieter than earthquakes and softer than Aurora, a layer that lives in the background of Earth's electromagnetic environment. Schumann resonances, they are not a new discovery. They are a natural property of our planet. Earth and its ionosphere form a kind of cavity, like the space inside a bell. The ground is one boundary, the ionosphere is another, and between them sits a thin shell of air. When lightning strikes anywhere on Earth, it sends electromagnetic waves into that cavity. Certain wavelengths fit neatly between the boundaries, and those wavelengths build standing waves, repeating patterns of energy that persist over time. Those standing waves are Schumann resonances. The fundamental frequency is around 7.8 Hz. Higher modes appear near 14, 20, 26, 33 Hz, and beyond. You do not need to memorize the numbers. What matters is the idea. Earth hums gently not in sound, but in electromagnetic rhythm. And that hum is continuously driven by global lightning and the electrical structure of the atmosphere. This hum can be measured. Stations around the world record the vertical electric field or magnetic field fluctuations in the Schumann band. When you look at their spectrograms, you see horizontal bands brighter at the resonance frequencies and darker in between. Those bright bands are the standing waves. Their intensity can vary over time, depending on global lightning activity and changes in the cavity itself. But here is the most important thing to understand. A Schumann station does not only hear the world, it also hears its own neighborhood. Local atmospheric conditions strongly affect the measurements. If a station is under heavy clouds, rain, or snow, if nearby thunderstorms are active, or if wind shakes the antenna, the spectrogram can light up with patterns that have nothing to do with a global change. These local effects can look dramatic. They can create spikes, broad blobs of power, or noisy bursts across a wide frequency range. This is why Schumann data is easy to misread. Many online interpretations treat every bright patch as a planetary signal. In reality, most of what people point to on a daily basis is local weather noise. Sorting true global signals from local effects requires checking station conditions, comparing multiple stations, and understanding what local interference looks like. Clear weather matters. If a station is in fair, stable conditions, and you still see an unusual burst that does not match typical local noise, then it becomes interesting as a possible global or regional signal. Even then, interesting does not mean proven. It means worthy of careful attention. During this current interval, some observers noted an unusual-looking burst in Schumann resonance data. Public scientific confirmation is limited, so we simply note it without conclusions. That sentence is deliberate. We are not rejecting what someone saw. We are not endorsing it as established fact. We are placing it in the correct category. A reported outlier, not a demonstrated driver. Schumann resonances are a diagnostic background tone, not a driver of earthquakes or geomagnetic storms. This is another place where timing can tempt the mind. When a strong solar flare happens and a CME is inbound, and an earthquake occurs around the same window, it is easy to want a single story that ties everything together. Schumann charts can feel like a convenient thread, but in careful science, we do not use a thread just because it is there. We test whether it belongs. What could space weather do to Schumann resonances in principle? Geomagnetic storms can disturb the ionosphere. The ionosphere is one boundary of the Earth ionosphere cavity. If that boundary changes height or density in a meaningful way, it could modulate resonance patterns. This is plausible at a basic physical level. But the cavity is also shaped by global lightning and local conditions. Separating a subtle ionospheric influence from background variability is hard. That is why the scientific posture here remains humble. We acknowledge the possibility of modulation. We acknowledge the difficulty of proving it. We avoid turning a single burst into a chain of cause. Even among researchers who study global electromagnetic environments, Schumann resonance changes are treated statistically. They look for repeatable patterns across many events, not a single chart on a single day. If a robust connection exists, It will show itself through those larger patterns, through careful controls, and through mechanisms that withstand retesting. So, for a listener tonight, what is the right takeaway? Schumann resonances are real. They are a natural electromagnetic hum of Earth. They are influenced mostly by global lightning and atmospheric conditions. They can also be influenced by local station weather. Sometimes an unusual looking feature appears. We notice it, but we do not build a story from it until the story has evidence. In a way, this is a lesson in how to keep wonder clean. Wonder without evidence becomes a mirror for anxiety. Evidence without wonder becomes dry. Schumann resonances invite both. They invite us to feel Earth as a resonant body. They invite us to learn the difference between noise and signal. They invite us to stay careful at the edge of what we know. If you like a soft imagery picture, you can hold this one. Imagine Earth as a quiet instrument. Lightning is the hand that keeps touching its strings. The ionosphere is the curved ceiling that shapes the echo. Most nights, the note is steady. Sometimes the room changes and the note shifts. We listen, we compare, we learn, and we do not assume that every shift has one simple meaning. This is the same posture we held with the solar storm and the earthquake. We notice, we measure, we stay honest about uncertainty. Tonight, Schumann resonances remain a background companion in the story, not its engine. They deepen the sense that earth and sky are layered systems, each with its own rhythms, each capable of subtle variation. But they do not require us to connect the rhythms without proof. In this broader interval of activity, another earth rhythm has been speaking as well. Kilauea. Kilauea is one of the most closely watched volcanoes on the planet, not because it is the most dangerous, but because it is one of the most continuously active and well instrumented. It sits on the big island of Hawaii, built by a hotspot that feeds magma upward through the crust. Over time, that magma has shaped layers of basalt like quiet pages in a long geologic book. Volcanoes, like Kilauea, do not erupt at random. They respond to pressure, to pathways opening or narrowing, to the slow movement of molten rock seeking equilibrium. When an episode strengthens, it is often because the system has found a cleaner route to the surface, or because pressure in the chamber has risen enough to drive a new pulse upward. During this current window, Kilauea has been in an active episode with lava fountains and flows contained within its summit and rift zones. For volcanologists, this is part of Kilauea's ongoing pattern. It is vigorous, but it is also familiar, the kind of vigor that this volcano cycles through again and again. We mention it here for context, not as a link, not as a cause, not as a sign. It simply sits beside the solar storm and the Alaska earthquake as another expression of Earth's own restless beauty. A flare on the sun, a quake in Alaska, a volcano in Hawaii, each belongs to a different system, each driven by its own primary forces, and each unfolding on its own timescales. Sometimes those timescales overlap on a calendar, and the overlap feels noteworthy. We can acknowledge that feeling without turning it into a chain. If you want a calm way to hold this, imagine Earth as a planet with many breath patterns. The tectonic breath is slow and deep-lasting years releasing in sudden slips. The volcanic breath is warmer and steadier, rising through conduits, sometimes spilling over invisible light. The electromagnetic breath is faint and continuous humming between ground and sky. None of these breaths require a single conductor to keep time. They are a choir of rhythms. So Kalawia's activity reminds us of that choir. It reminds us that Earth is not only a receiver of space weather, but a generator of its own energy, its own motions, its own luminous events. The lava glow in Hawaii is a cousin, in a way, to the auroral glow in high latitudes. Both are forms of light, born from energy, moving through matter. Both can be watched in quiet awe, and if you are far away from both, you can still feel the meaning. You live on a planet that is alive in layers. Now we lift our eyes back to the night sky, to the part of this story you might actually feel with your senses. Aurora. If the incoming CME couples strongly with Earth's magnetic field, no AA expects geomagnetic activity centered around G3 conditions with a smaller chance of a brief G4 peak if the magnetic orientation turns clearly southward. When storms reach that strength, the auroral oval widens and the zone of possible visibility expands farther from the poles. This is an evergreen truth of space weather. Aurora is most common at high latitudes because that is where Earth's magnetic field opens most directly into space. The poles are the gateways. When the magnetosphere is pressed and energized, those gateways widen, and the oval spreads. In the northern hemisphere, that means brighter and more frequent aurora across much of Canada and Alaska and into the northern tier of the United States. It can also mean stronger visibility across Scandinavia, Iceland, Scotland, and higher parts of continental Europe, depending on the storm shape and the local night. In the southern hemisphere, the oval expands too. Areas near the southern tips of New Zealand, Tasmania, and the far south of South America sometimes enter the zone when storms are strong. The presence of aurora there is less discussed online, but it is the same physics mirrored across the planet. Because this is a living system, we always speak in chances. Storms are patchy. Clouds hide the view. Magnetic orientation can soften what might have been brighter. And sometimes the oval shifts east or west, favoring some longitudes over others. So aurora is never a promise, only an invitation. If you feel like accepting the invitation, it helps to keep the approach simple. Find darkness away from city lights. Even a short drive can change the sky. Let your eyes adjust for 10 to 15 minutes, because human vision in low light needs time to wake up gently. Then face north if you are in the northern hemisphere, or south if you are in the southern. The aurora often begins low on the horizon and grows upward as activity rises. You may see a pale glow, first like a soft mist. You may see a thin arc steady and quiet. If activity strengthens that arc, can curl into curtains that lift and fold, and sometimes ripple quickly like wind in silk. A camera sees more in dim light than our eyes do, especially at first. If you have a phone, use night mode if it includes longer exposures. If you have a camera, try a few seconds of exposure at a moderately wide aperture. You do not need perfection. Aurora is generous to any tool that can stay still for a moment. Even a simple shot can reveal color where your eyes saw only brightness. And if the sky stays ordinary, for you, that is still part of the story. Aurora depends on a chain of conditions. Solar wind must be strong. Magnetic orientation must couple. Night must be clear where you stand. And the oval must drift over your latitude. If any link softens, the view softens too. There is no failure in that. You are not missing a secret. You are simply living under a sky that varies. Now, since we are here, let's talk about what Aurora is made of in the simplest and most beautiful way possible. When charged particles come down along magnetic field lines, they collide with atoms high in the atmosphere. Those atoms briefly jump into higher energy states, then relax back down. When they relax, they release photons, light. Different atoms release different colors, and even the same atom can release different colors depending on altitude. Green comes mostly from oxygen lower, in the upper air, around 100 kilometers high. Oxygen there relaxes quickly, giving the sky its most familiar shade. Red comes from oxygen higher up, where the air is thinner and relaxation is slower, so the red glow often appears above green, or as a faint wash in very strong storms. The faint blues, or purples, belong to nitrogen, usually at lower altitudes or at the edges of active curtains. The colors are not paint in the sky. They are atoms resting back into themselves. This is why Aurora feels alive. You are watching matter respond to energy instantly and honestly. You are watching Earth's atmosphere reveal its own ingredients. You are watching a magnetic process become visible as a moving light. In a strong storm, the colors can change with time. A curtain might open green blush with red at the top, then fade to gray as activity softens. Sometimes, the eye sees only a pale white glow, while the camera shows the rich colors that were always there. All of it is real. All of it is physics made gentle. If you do see Aurora, there is a quiet way to take part in something larger without leaving the calm of the experience. If you happen to photograph the Aurora, you're also helping science in a small way. A simple note of time direction and what you saw can join thousands of quiet observations worldwide. Citizen science for Aurora does not have to be formal. The world is full of observers who share their sky notes with networks that study auroral boundaries and storm evolution. A photo with a timestamp, a rough location, and a direction facing north or south can help map the oval's reach. It helps refine models. It helps future forecasts. You become one gentle data point in a planet-wide listening. You do not need to do it, but if you like the idea, it is there. And whether you observe or not, the meaning remains the same. Aurora is one of the clearest ways an invisible system lets itself be seen. We live inside a magnetic field. We move through a solar wind. Most of the time, that relationship is silent. During a storm, the silence becomes a glow. It is easy to forget this relationship when we are busy. We think of weather as clouds and rain. We think of earth energy as quakes and volcanoes. We do not always think of the sky above the sky. Aurora reminds us, it reminds us that Earth is not isolated. It reminds us that our atmosphere reaches out into space. It reminds us that our planet has a kind of protective skin that flexes but does not break. And in the quietest sense, it reminds us that beauty can emerge from pressure without becoming danger. So if you feel like looking up in this arrival window, do it gently. Bring a warmer layer. Bring patience. Let your breath slow as you wait. Sometimes the sky gives you a show. Sometimes it gives you a calm, empty darkness that is beautiful in its own way. Either result is a true part of living under an active star. Now we let the facts rest for a while, and we let the images breathe. Imagine the sun far off in the dark, not as a harsh flame, but as a steady lantern with tides beneath its surface. Its light moves across space the way warmth moves through a quiet room, slow and faithful. And inside that light, there are moments when magnetism loosens and lifts, sending a wave outward like a soft hand opening. The wave travels through the solar wind, and the solar wind is a river without banks. It flows everywhere, filling the space between worlds, carrying tiny charged grains of the star's breath. The wave does not rush. It moves on a long path, a path measured in millions of kilometers. Yet it feels intimate when it reaches the place we live. Earth waits inside its own invisible shelter. The magnetosphere is a quiet bubble, a gentle boundary that knows how to flex. It is like a shoreline that has spent a lifetime meeting tides never startled by their arrival, only responding with its own calm shape. When the wave touches that shoreline, the boundary leans inward. It holds the pressure with patience. It gathers energy the way a lake gathers wind, and then it releases that energy in slow pulses, sending it toward the poles where the air is thin and open. High above atoms rest in near-empty cold. Oxygen, nitrogen, the quiet characters of our sky, waiting without worry. When particles spiral down along magnetic lines, they meet these atoms softly, and the atoms brighten, then return to themselves. The light is not loud. It is a gentle, remembering a signal that something invisible has passed through. You can picture the aurora as a curtain made of breath. It hangs in the upper night, and when the storm is kind to us, the curtain stirs and folds. Sometimes it glows green, low in the sky, like a calm fire in distant grass. Sometimes it blushes red, higher up, like a faint sunrise that forgot to become day. Sometimes it carries a whisper of blue or purple at the edges, a little hush of nitrogen in motion. And if you are not there to see it, the sky still knows. The conversation still unfolds above forests, above oceans, above sleeping towns. It happens whether or not anyone watches, and that is part of its peace. Below the air, the ground holds its own long rhythm. A tectonic boundary shifts not with intention, but with physics. Stress builds like a slow inhale through years, and then releases in a deep exhale that lasts only a moment. Aftershocks are the small, settling breaths that follow the crust, finding a new way to be still. Somewhere on the planet, a volcano keeps a warm pulse. Lava moves through hidden corridors and sometimes emerges in quiet fountains, glowing the way Earth glows when it is being itself. None of these layers need to be tied into a single chain. They can be neighbors in time without being parents of each other. They can be simultaneous without being the same story. That is how nature is many rooms in one house, each with its own clock. So let your mind walk through the house softly. A star breathing in cycles, a wave traveling without haste, a field around Earth flexing and holding, a sky that can glow when touched, a ground that can release when ready, and you in the middle of it, all safe and small, in the best way, tucked into a planet that knows how to endure. If any thought feels sharp, let it soften. If any detail feels heavy, set it down. You do not need to carry the universe to rest in it. You only need to feel that you belong to it quietly, the way a shoreline belongs to the sea. Stay with your breathing. Let the night be kind around you. Let's gather the journey in one quiet view, and then let it fade into rest. In this current window, the sun has been especially active. A recent upper M-class flare released energy from a tangled magnetic region, and a coronal mass ejection lifted away, with it expanding outward like a slow, luminous cloud. Models suggest the cloud is aimed close to Earth direct, so our planet is likely to feel its arrival as a period of stronger space weather. NOAA centers expectation on a geomagnetic storm near G3 conditions, with a smaller chance of a brief G4 peak if the magnetic orientation inside the cloud turns strongly southward. We hold that as a range, not a verdict, because the final key is not speed or density alone, but the direction of the magnetic field carried within the CME. When that direction couples well with Earth's field, the magnetosphere flexes more deeply, energy transfers in more efficiently, and Aurora expands. We pictured the magnetosphere as a quiet shoreline, and that picture is true. It bends, it stores, it releases, it breathes with the solar wind, and when the breathing is strong enough, the upper atmosphere lights gently in response. Green from oxygen lower in the high air, red from oxygen higher up, and faint purples and blues from nitrogen. Not paint, but atoms resting back into themselves. We also came down to Earth. USGS recorded a magnitude 7.0 earthquake in Alaska, followed by a dense aftershock sequence. We held that story in its proper home. Earthquakes are mainly internal releases of tectonic stress built over long spans of time, and aftershocks are the crust settling into a new balance. The timing of a quake beside a solar storm can feel striking, but timing is not causation, and we keep that boundary clear, so wonder stays clean. In a subtler layer, Schumann resonances reminded us that Earth has a soft electromagnetic hum, shaped mostly by lightning and the atmosphere. Some observers noted an unusual-looking burst during this interval, but public scientific confirmation is limited, so we noted it without conclusions. It remains a background diagnostic tone, not a driver of storms or quakes. And in another Earth rhythm, Kilauea has been active as well, a warm pulse rising from a hot spot, another reminder that Earth generates its own energy in many forms. 3 major threads, one span of time, and no need to force a knot between them. If you feel like looking up during this arrival window, do it gently. Find a darker sky. Let your eyes adapt. Look toward the nearest pole and watch for a soft glow that might lift into motion. If you photograph it, you become part of a quiet web of observation around the world. And if the sky stays ordinary for you, that is also true and also beautiful. Aurora is an invitation, not a promise. Thank you for traveling through this with me. If you'd like to stay close to these quiet science updates, you're welcome to subscribe and to return whenever you want, a calm way to meet the larger world. We will keep listening to the sun to earth and to the delicate boundary between them, not to chase headlines, but to rest inside a reality that is alive and often luminous. For now, let the details drift away. You have done enough by listening. You do not need to hold any numbers, only the feeling of a system that breathes, a star releasing waves in its cycle, a planet receiving them in its field, a sky that can glow softly, a ground that settles slowly, and you safe in the middle, letting the night be kind. Good night